Hi, welcome to this module. In this module we will be discussing about how to pattern a metal which is deposited on an oxidized silicon substrate. We will also see if it is not an oxidized silicon substrate and if it is a glass substrate, then also how can we pattern the metal on it, and the applications would be for a patch electrode that you can attach and you can get the signals out of it. Having said that, we will also have one module which was already you have seen, which is on COMSOL simulation, right. We have recorded that, and in that you will be able to see how much the pressure one has to give on the skin, so that it will not harm either the sensor or it will not poke the skin. So, if you take the EEG electrodes, then there are several kind of electrodes that as you know now. There are spike electrodes, there are wet electrodes, there are dry electrodes. So, for the spike electrodes in particular and for other electrodes also, once you place on the scalp, the pressure should be not that much that it will start poking your scalp or skin, right. So, that how we will know when you design a band how much pressure should be given. You can design, you can understand by performing simulation using COMSOL, which one of the TA has already taken in this particular class. So, let us come to this module, and as you already know about lithography, earlier in we have discussed this thing earlier module, that with when you want to perform a lithography, you have to start with a wafer which you have to go for cleaning. There are two types of cleaning, RCA1 and RCA2, and it is also called piranha cleaning. Then you have to go for pre-bake to remove any kind of moisture from the wafer. Go for photoresist spin coating. Photoresist can be two types, as you know, positive and negative photoresist. Then you go for soft bakes. If you use positive and negative photoresist, generally soft bake is done as 90 degree centigrade for 1 minute on hot plate. If it is not hot plate and if it is oven, then the temperature would be same, but the time would be different. Then you have to take a mask, aligned and exposed, you already know. Finally, you have to develop the photoresist and perform a hard bake. Hard bake is also called post exposure bake. Now, you also know that particular term. Post exposure bake is done as 120 degree centigrade for 1 minute on hot plate. After that, you can develop the metal or whatever the material is on the top of the wafer, and you can understand whether the part has been patterned perfectly or not using the pattern inspection method. So, these are the steps in lithography. I am just before I start giving you the process flow, I wanted to just help you to recall what photolithography steps are involved. What are the steps? In case of photoresist, you have to photoresist, and as you already know that if this is a mask which is your bright field mask, if I use positive photoresist, I can replicate the pattern. If I use negative photoresist, I would have replicate of that pattern. Okay, the English is a little bit funny. So, you can replicate the same pattern here, but this is the opposite of the pattern that you are getting in the negative for photoresist. In another terms, or in as per the book terms, what you will read is when you use a positive photoresist, the unexposed region would be stronger, right, and the exposed region would be weaker. If you take a negative photoresist, the unexposed region would be weaker and the exposed region would be stronger, correct. So, this is how positive and negative photoresist works, that also you know. Now, let us take an example of patterning a metal on an oxidized silicon substrate. So, I will take so what I want finally, okay. First we have to understand, finally we want oxidized silicon substrate, that means you should have oxide. Let us pattern oxide. When you say oxide, it is silicon dioxide, right. Why you use silicon dioxide and how you grow silicon dioxide on silicon wafer? Now, you know that process as well, right. First is how silicon came into existence, that means that how we are developing a wafer, that you know the process CZ process and FZ process, right. Czochralski or float zone technique, we have seen from the sand how the silicon wafers are fabricated, and once your silicon wafer, right, you have a single side polished silicon wafer and double side polished silicon wafer. Here we are using single side polished silicon wafer. Single side polished silicon wafer is less costly compared to double side silicon wafer. Now, when you talk about silicon dioxide on silicon, you again know that there are several process. One is your thermal oxidation, right. Thermal oxidation, you can grow silicon dioxide. If you talk about thermal oxidation, again you know from our previous lectures that there can be wet oxidation and there can be dry oxidation. Other way of depositing oxide instead of growing oxide would be using sputtering, right. You can sputter the silicon dioxide onto silicon wafer. Another way of growing silicon dioxide depositing would be PECVD. We have not taken in this particular course the details about CVD techniques, but just to help you out that there are different methods to grow silicon dioxide. This method is called plasma enhanced chemical vapor deposition. Okay. So, plasma enhanced chemical vapor deposition, thermal oxidation and sputtering are three known methods, right. There can be other methods as well, but this is these are three answers if a question is there that what kind of method you can use for depositing silicon dioxide on silicon wafer. Now, having said that, so we have a silicon dioxide and our thickness of silicon dioxide is about 1 micrometer. Okay. Silicon wafer is 4-inch silicon wafer. If you have 4-inch silicon wafer, the thickness would be 450 micrometer to 500 micrometer, okay, 450 to 500 micrometer. All right. Now, on this silicon dioxide, we want a patch that looks like this, okay, and this would be our metal. Okay. This will be our metal, let us say gold, okay. Gold is there. So, if you see that the top view, it will look like so the dotted region is your metal, which is your gold, and this one will be your silicon dioxide. This is gold on silicon dioxide, and this is your silicon dioxide. Okay. You want to use this, it can be used for a lot of applications. One can be patch, but there are other applications. Right now what we are interested in, how can we design or pattern the gold on silicon dioxide. So, let us start the process. The first step, as you already know, let me draw it. Okay, this is a cross section of a silicon wafer. In case if somebody asks you in an interview or in your exam, you have silicon wafer, you grow silicon dioxide, then you deposit metal on silicon dioxide, then you spin coat photoresist on silicon dioxide, spin coat photoresist, photoresist let us say is represented by X. What is this? Photoresist. What is this material, let us say metal, this one you know it is SiO2, this one, right. Now, after you spin coat photoresist, what is the next step? Come on, you should know by now. Next step would be soft bake, exactly, that is correct, 90 degree centigrade 1 minute on hot plate. Yeah. After that, what is the next step? You should have been answering the question while I am talking to you guys, that the next step would be to load the mask, right, load the mask, silicon dioxide, metal, photoresist and your mask. How should mask look like? Mask will look like this. If I am using positive photoresist, then a mask will look like this, but let us say in this case, just to make it easier, I am going to use negative photoresist. Okay. So, if I am using negative photoresist, mask should look like the one that I am drawing right now. Okay. If I would, this is a mask, if it is negative photoresist, but if it was positive photoresist guys, then our mask should look like dark film mask, right. It will look like a dark film mask, because you know that if it is positive photoresist, then the area which is not exposed by UV light will be stronger. So, if I want to use positive photoresist, my mask should be similar to what I am right now drawing, but if I am using negative photoresist, my mask can be bright field mask. So, understand this thing, if somebody writes that with positive photoresist we have to use bright field mask, with negative photoresist we have to use dark field mask, that is not correct. Okay. It is not correct. If you have a mask, then you have to understand which photoresist you can use so to pattern, or if you have photoresist you can design the mask accordingly. So, in this case if you see the slide, that if I use negative photoresist, but if I want to use a positive photoresist, then my mask should be the one that I am showing it to you here, right. So, why? Because in negative photoresist if I am using, then the unexposed region which is here would be weaker and the exposed region would be stronger, In case of positive photoresist, the unexposed region would be weaker and the exposed region would be stronger. Sorry, is it correct or not? No, it is not correct. The unexposed region would be stronger, and the exposed region would be weaker in case of positive photoresist. In case of negative photoresist, the exposed region would be stronger and the unexposed region would be weaker, correct. So, depending on the negative photoresist, positive photoresist, you can change the mask, alright, cool. Now, once we have the mask, then what is the next step? You have to load the mask and align it with the wafer. Now, every time we use this word aligning, what does aligning means? You have a mask here, okay, and these are alignment marks. This is the pattern on the mask, alright, is a pattern on the mask. You assume that this is entire thing is dark, okay, entire thing is dark, these two patterns. So, now you have to make sure that the alignment of the wafer is correct with respect to mask, it is not tilted. Second thing is it should be in the center of the wafer, since it is the first mask process or one single mask process. So, it should be in the center of the wafer, right, it should not be tilted, it should not be towards too much towards one direction, not towards too much towards other direction, that is why this is x, and tilt is our theta, right. So, we can, that is why if you recall about mask aligner, we can move the mask in x direction, or we can move the wafer in x direction, y direction or theta. You have option of either moving the wafer, or you can option of either moving the mask, right. So, this is the alignment. So, once you perform the alignment, what is the next step? After alignment, you have to expose the wafer, and exposure is done using UV light. So, you will have UV light exposure of this wafer, UV light, all right. After that, you have to unload the mask and develop photoresist, unload the mask and develop photoresist. So, if you do that, if you perform the developing step, what you will have? You will have a wafer, which is our oxidized silicon wafer with gold coating on it. Now, I am still not going too much into depth about the fabrication methods. Otherwise, you instead of, when I say gold, gold is always comes with chrome layer at the bottom, thin layer of chrome that will improve the adhesion of gold onto the oxidized silicon substrate. Okay. But I am not going into depth of this. So, right now you assume there is a metal and which is gold. So, on gold you have your photoresist. Okay. On gold you have your photoresist, and photoresist will be shown by X. Now, you understand the photoresist after development. You see here that because we are using negative PR and our mask is this, that is why the exposed region is stronger and the unexposed region is weaker. You can see here the unexposed region is weaker because this is our negative photoresist, correct. After this, our next step would be hard bake or post exposure bake, 120 1 minute hot plate, correct. So, if I go for hard bake at post exposure bake, next step would be to etch metal. What is metal in our case? AU, right. So, if I dip the wafer in AU etchant, okay, what will I see? I will see, again understand, the oxide layer below it will not get affected because the etchant for gold will not affect the oxide. Oxide will get affected mostly when you use HF based etching material. So, what you have here now? You will have the gold etched from the area which was not protected by photoresist, is not it? You see here. Now, you have photoresist, of course, negative photoresist, let us write negative, and you have gold, you have SiO2, you have silicon, and here you see that the gold is etched, right, gold is etched. Next step after this, what is the next step? Everyone knows, right. Next step would be that you take this wafer, of course, when I drawing is, you take this wafer and dip it in acetone. If you take this wafer and dip it in acetone, what we will have? We will have photoresist will get stripped off, photoresist will be stripped off, and you will be left with metal patterned on oxidized silicon substrate, is not it? You have metal on oxidized silicon substrate. This is what we wanted. Let us see. We go back you see, easy. So, this is how we can pattern the metal on an oxidized silicon substrate. Also there is an alternative, instead of using oxidized silicon substrate you can perform everything if you have glass. So, if you have glass here, then you do not have to grow oxide here, because glass itself is silicon dioxide. So, directly you after glass you can start with this step, that you deposit gold on glass, and remaining step remains same. The only difference is, if you use silicon substrate you have to grow oxide, because silicon is a semiconductor and oxide will help to help as an insulator between metal and semiconductor. But in case of glass, since glass itself is an insulator, you do not have to separately grow silicon dioxide on the glass. You got it. So, I hope that this helped you to understand how to pattern the metal on an oxidized silicon substrate. Now, let me show you to you. If you see my hand, I am holding a wafer. Can you see? Yeah. See, I am holding a wafer that has been patterned. You can see gold is patterned on an oxidized silicon substrate. If I show it to you in a different manner, see, gold is patterned. This is a different pattern. Okay, this is one pattern. There are two wafers. It is not magic. There are two wafers. Yeah, both are oxidized silicon wafer. Okay, and you see here there is one pattern that you can see on an oxidized silicon substrate. Process was same. You take a silicon wafer, you oxidize it. You see in the back side, the color is different, right. That means there is a oxide on silicon wafer. When you when you grow oxide on silicon wafer, the next step would be that you deposit gold on the oxidized silicon wafer, then spin coat for positive photoresist or negative photoresist depending on the mask that you have to use, soft bake, align the mask, expose it with UV light, develop the photoresist, hard bake, then etch the gold from other area except the area which is protected by photoresist, it will not get etched. Finally, you have to dip this wafer in acetone to remove the photoresist that will be on the top of this layer, and that is called stripping step. When you dip the wafer in acetone, you will have this particular wafer. Again, please understand that for getting any kind of pattern, after every etching step you need to rinse the wafer in deionized water, and after rinsing the wafer you have to dry the wafer with nitrogen. Right. So, nitrogen is a gas that can, or air can be used for drying the wafer, and DI water is to rinse the wafer. This is by default is a step that is used for during the photolithography process. No wafer can be processed if it is not rinsed or dried before it can go to next step. Okay, you should not go to next step before the wafer is rinsed and dried. This is very important step that you have to understand, that every time when we draw we do not discuss about it, but it is by default it is understood that when you get a new wafer you always have to dip in HF to remove the native oxide, then you have to rinse it, then you have to dry it, then you have to pre-bake it at 120 degree or higher temperature, so that to remove the humidity from it, right. It is known. So, generally when you see in the process flow they say take wafer, grow oxide, but in between you have to understand that when you take the wafer and grow the oxide, this process is already there which is called RCA1 RCA2 cleaning. Okay. Then you have a oxide. After you oxide you deposit the metal, there is no chemical involved here, right. You take the oxide and grow or deposit a metal. Okay. Now you spin coat photoresist, again you do not have to do anything, soft bake nothing, expose, align and expose nothing, develop photoresist, right. So, chemical came. After developing you have to rinse it, dry it, then go for hard bake. Okay. Then take it, then etch gold. Let us say in this case when you etch gold, chemical is involved. After you etch it you have to rinse it, dry it, okay. Then you have to dip it in acetone, again chemical is involved. You take it out once the photoresist is stripped off, rinse it with DI water or wash it with DI water and then dry it with nitrogen. You understand, whenever a chemical step is there, you need to take care of it. If you want to understand this recipe in detail, there are a lot of photo lithography examples that you can find it from YouTube videos. A lot of videos available, but what I was thinking as a part of this particular course, as some of the modules that I have taken. Of course, the detail will be taken by Dr. Mahesh on in the area of neuroscience and neuroinstrumentation, but what we were able to show it to you is right from the oxidized silicon substrate all the way to patterning the substrate. There are many steps that are involved in. We try to cover this through these modules. So what you learned in this instrumentation side, you have seen how silicon is made, you have seen how oxide is grown, you have seen different PVD techniques, whether it is thermal evaporation, e-beam evaporation or sputtering. Then you have shown in the thermal oxidation technique, which is silicon dioxide is grown, you have seen wet and dry. Then you have seen wet etching technique, by which we are etching either BHF or either oxide, or you are etching gold. And also we have seen how silicon can be etched with example of KOH. Then we have seen how can we pattern the wafer onto the using the photolithography technique that we have seen. Then we have seen how the COMSOL simulation can be used for simulating a pressure applied on a skin. Then we have seen how to develop an electronic module using a multi-sim technique, and then we have also seen how, if you have the EEG electrode, what is the complete electronics that is there to acquire the signal and to process the signal. So this was the part of the neuro instrumentation that we wanted to teach you. Again, understand it's an introductory neuroscience and instrumentation. It is not an advanced level. That's why we kept it as a more of a introduction, and we covered the basics around it. Once you are familiar with the technique and you are familiar with the introduction of the neuroscience, we will try to see if we can take an advanced course on the same subject. Till then, if you take care. If you have any question, feel free to ask us via the NPTEL forum. Bye.